Hey, everybody. Thank you for joining us today for our talk on mapping detection coverage. My name is Johnny Johnson. If you go to the next slide, Jared. Hi, my name is Johnny Johnson. I'm a consultant at SpecterOps. I do defensive security research as well. JSecurity 101 is my handle for pretty much everything. So you can find me on Twitter, Medium, things like that. I used to be a senior threat researcher at Red Canary, and I'm one of the hosts for the Detection Challenging Paradigms podcast. I'll pass over to you, Jared.
Yeah, and I'm Jared Atkinson. I'm the chief strategist at SpecterOps, also a host of Detection Challenging Paradigms podcast. This could almost be like a little bit of a pre-prepared podcast episode, you might say. So rather than just being an open format like we usually use for the podcast, we'll kind of we have a specific topic that we want to touch on, but I think there will be a little bit of a kind of an informal air to the talk, to where we kind of banter back and forth. Maybe there will be some conversation. I got my start with the U.S. Air Force Hunt Team, so that's where I kind of started. Then I became a consultant after 5 years in the Air Force. Now I'm again at SpecterOps, and I used to kind of do open source development, but now I'm more kind of going forward and kind of writing about my thoughts, right? And so there's this blog series that I've been writing called On Detection, and the outcome of that is implemented in this talk. So I'm going to try to cover some of those topics. Okay, so why are we talking to you about this idea, this mapping detection coverage idea? So I've noticed over the past year, maybe couple years, that there's been this kind of thirst or hunger for consumers in the detection space to be able to really quantify or get a good idea for whether or not their detective controls actually solve the problem that they were built to solve. So we kind of saw this really start to take off when MITRE ATT&CK first came out. Roberto Rodriguez released a blog post that was talking about building a heat map for MITRE. So it was like, I have a detection for Kerber roasting, and I'm going to color in that square on the matrix as green. But one of the problems that Roberto really pointed out is it's really difficult for us to understand whether our squares should be red, orange, yellow, green. We don't know what makes something green, and so that's been a problem that we've consistently been trying to solve. I've noticed that this is a problem that people are also trying to solve with red teams, right? And there's a number of reasons why I think that red teams, while they're good for some things, they're not really great for trying to answer the question of, do I detect this attack technique? One of the reasons is that they don't provide a representative sample set of all the variations that are possible for an attack technique. And so the question is if red teams don't solve that, then what does, and what would a good process look like? Okay, so the question, one of the big problems is that vendors seem to hand wave this. So they say we detect credential dumping, but they don't actually provide any evidence that they have a comprehensive detection for credential dumping. So you don't really know how to interpret that. And then there seems to be this feeling that detection is more of an art than a science. You've probably heard somebody say that. And to me, that seems almost like it's we haven't figured out how to make it into a science. And so we kind of use this art term. We throw it around as if there's no rules that can be followed. And I think that there are. We think that there are anyway. So the question is can we establish a scientific process, or at least a somewhat scientific process, and try to figure out how do we discern whether or not our detection rules actually comprehensively provide coverage for the thing, for the behavior or technique that we're actually targeting. This question kind of leads us to two sub questions, right? So it's a good question, but it's not something that you could just answer on its face. The first sub question, which we're going to really kind of hit on in this talk, is the question of, how do I know that my sensory capability, so my EDR, whatever it is that I'm using to collect telemetry from my environment, so the thing that tells me what's happening in my network, how do I know that my sensory capability is providing me the information that I think it is? If this behavior occurs, will I know that it happened? If the behavior doesn't occur, will I be able to discern that it didn't happen, right? And then from there, then you can start to ask the question of, how do I know that my detection rule is calibrated for the threat that I'm trying to detect? Okay. So the way that I think that we can start to look into this is through tools. So I view tools as an instantiation of an actual attack technique. So you have this abstract concept, which is an attack technique: LSAS, memory dumping, Kerber roasting, WMI, lateral movement, service creation for lateral movement. There's a bunch of different attack techniques, 200 and something. But those attack techniques must be instantiated in the form of tools, right? And there's many different ways that tools can be instantiated. And so if we could start to analyze how tools are constructed, we can start to get an idea for the differences between tools. And some tools are more different than others from each other, right? And so the first tool we'll look at, we're going to focus on LSAS memory dumping, so credential dumping from LSAS. The first tool we'll look at is a tool called out mini dump. This was written in 2013 by Matt Graber. And really what Matt was trying to do was kind of re-implement a capability that's inherent in proc dump, which is one of the sysinternals tools, which is the ability to dump, generate a crash dump or a memory mini dump for a process. And specifically because we're trying to target credentials from LSAS, we're targeting LSAS in this case, but generally speaking, this would apply for any process that you're trying to generate a crash dump for. And so all you do is, use PowerShell to enumerate processes, in this case LSAS, and then you pipe that into out mini dump and it generates a file for you. Okay. Now, when we actually look at how out mini dump works, we observe that there's kind of three major functions that are being used, right? The first is a function called it's implemented by the DLL, ntdll, and it's called int query system information. This is being used to enumerate processes in order to identify LSAS, the LSAS process, and identify its process identifier, because that's a necessary bit of information for the next component. The next thing that it does is it has to open a read handle to LSAS. A read handle is just this thing that allows the application to interact with LSAS, which is basically processes are stored in the kernel, and so you have to run through the kernel and ask for permission to interact with it. And in order to do that, it uses a function called kernel32 open process. And then lastly, it's going to actually generate the crash dump using a function called debug help mini dump write dump. And so that's how out mini dump actually works, right? So that's our general idea. There's three things that have to happen. You have to get the process identifier of LSAS. You have to open a read handle to LSAS, and then you have to actually generate the crash dump. So we use ntdll, nt query system information, kernel32 open process, and debug help mini dump write dump in order to achieve those objectives, right? And that's ultimately what we're doing. Now, if we look at a second tool, which is called sharp dump. So the first tool, out mini dump, was written in PowerShell. This tool is written in C#. But Will Schroeder, otherwise known as Harmjoy, he actually wrote this in 2018 and purposely basically copied the code from out mini dump. So it's like they call it a port in kind of programming lexicon. But the idea is that he wanted to move away from PowerShell. There was a number of different security enhancements and logging features added to PowerShell that he wanted to avoid. And so he moved from PowerShell to C#, but he basically just used out mini dump as a template and then just copied that over. And C# and PowerShell are very similar, so it's a pretty easy process, right? But generally, this does the same thing, right? So if we were to look at the functional analysis, we would notice that the same three functions are being used by sharp dump to do the same thing, right? So they use ntdll, nt query system information, they use kernel32 open process, and debug help mini dump write dump to achieve those same three things, right? Enumerate lsas.exe's process identifier, open a read handle, and generate a crash dump. Okay, and we could actually literally compare the source code. Luckily, both of these tools are open source, and so we could compare the source code, and we see here in the first box, the first comparison, we see that they're dealing with a process object. This is a .NET concept. That process object has the process ID and generates the process handle. And then in the second comparison, we see mini dump write dump being called in both cases. So we see that that's equivalent, right? So that's like we could literally compare the source code to see that they're doing the same thing. Okay, and this introduces this idea that I call synonyms, and this is something that I derived from Aristotle. So Aristotle talks about in the Categories, which is one of his famous books on like ontology and metaphysics. The idea is that if you have two instances, in this case we're talking about tools, like hacking tools, you could say, but he was talking about any object in the world, right? If you have literally two unique instances that are literally different, but at some level of abstraction they correspond. So for instance, he talks about man, which is like humans, right? And ox. they both are animals, right? And so you could say that they're synonymous from the perspective of them both being animals. But in our case, what we're saying is we have out mini dump, one tool, and we have sharp dump, another tool, and they're synonymous at the functional level. So they're literally different tools. One's written in PowerShell, the other's written in C#, but they call the same functions, and so they're functionally synonymous, right? Now, synonyms are actually pretty interesting because there's a number of levels of abstraction, which we'll get into in this talk, that we could look at, and we can actually use this as a heuristic for similarity. So tools that are functionally synonymous, you could say that they're more similar to each other, heuristically, than two tools that are not functionally equivalent or functionally synonymous, right? And so the idea is that tools that are synonymous at higher, less abstract levels, they can be considered more similar to each other, and tools that are only synonymous at lower, more abstract levels are more different, right? And so that's pretty nice. Now, the cool thing is that when we start talking about instances, right, so these tools, there's actually an infinite number of tools that can be used or can be created or developed to achieve LSAS memory dumping, this attack technique. And so there's an infinite number of them. And we can't test or we can't validate that we can detect an infinite set because it's infinite, right? But what we could do is we could generate a representative sample set, which we'll get into, which allows us to approximate our coverage across the set, and synonyms are going to help us do that. This is similar to medical testing. If a pharmaceutical company comes up with a new drug, they're not going to just test me and say, looks like it worked on him, we're good. What they're going to do is they're going to get a representative sample population, which is generally representative of the world population, and then they're going to test it across that representative sample set to see if there's any unforeseen side effects or unforeseen problems, right? We should do the same thing when we're doing detection testing, a representative sample set of the possible variations. Okay, so we can actually start to map this out. So again, out mini dump and sharp dump are literally different tools, but we can map it out and we say, here's out mini dump, here's sharp dump. They actually call the exact same functions. So one layer of abstraction away from the literal layer, I guess you could say, we see that they're the same. And so now we know that the differences between the two are relatively superficial. So if you have a detection rule that detects out mini dump but not sharp dump, you probably have something like a tool-based detection or a signature, right? That rule is not very robust to change, right? And generally speaking, we would want our detections to be able to at least be able to detect this level of difference, right? Okay, so that brings us to a third tool, Dumpert. And Dumpert's actually a little bit more different, right? And so Dumpert was written by the team at Outflank, which is a consultancy in the Netherlands. They do at least red teaming that I'm aware of. And it was written in 2019. And one of the things that they did to change it up is they took the Win32 API functions that were being called by out mini dump and sharp dump and Mimikatz, and they replaced them with syscalls. And what they found is that when you make a syscall, which is like a direct call to a kernel function from user mode, what they found is that when you do that, there's a subset of EDR sensors that are naive, right? And they don't see that level of depth. And so it actually creates an evasion opportunity, right? And so what we see here, if we were to analyze, Dumpert's doing the same thing. It has to get LSAS's process ID, it has to open a read handle, and it has to generate the crash dump. But it's calling different functions in order to achieve those objectives, right? So we call, instead of ntdll, query system information, we call the syscall, right? And instead of calling kernel32 open process, we call the nt open process syscall. And then we see that they call the same mini dump write dump function. So debug help mini dump write dump. So we see that there's two changes, right? But the changes aren't drastic. They're just slight. They just varied the functions slightly, right? And this creates an opportunity for us to introduce a higher level of abstraction than the function. So we have the literal level, which is all tools are different from each other. If they have a different cryptographic hash, you might say then you could say that they're literally different. But then you could also say, hey, these two tools are literally different, but they call the same functions, and so they're functionally synonymous. Now we're in a situation to where we call different functions, but those functions are being used to achieve the same objectives, or as I call them, or we call them, operations, the same operations. And so we have, for instance, this is out mini dump along the top, and then we have Dumpert along the bottom. We see ntdll, nt query system information, versus the syscall to nt query system information. Those are different. we see kernel 32 open process versus syscall open process, int open process. But if we were to look one level of abstraction higher, we would see these operations, which are process enumerate. We have to enumerate the processes so that we could get the process identifier. Process access, we have to open a handle, a read handle specifically to LSAS or to the process that we're targeting. And process read, we have to read the memory of the process. And to some degree, the function that's being used to achieve that is irrelevant, right? Because the attacker cares about achieving the objective, not what function they use. But if they could find a situation to where using one function provides some sort of evasion opportunity, then that gives them an advantage, and we need to be aware of that. Okay? And so we can say that out mini dump and dumpert, while they're not functionally synonymous, they're operationally or procedurally synonymous. They call the same operations in the same order, despite the fact that they use different functions. Okay? Now this introduces an interesting concept. It's like, how can you call two different functions and achieve the same outcome? Well, there's this thing that I'm calling the function call stack, which is when I call the Win32 API function kernel 32 open process, which is how we open a handle, what we find is if we actually investigate in like IDA or some sort of disassembler how this works, when you call kernel 32 open process, it doesn't actually perform the action immediately. It actually calls another lower level function called API MS WinCore process threads open process. That then calls kernel base open process, which then calls ntdll nt open process, which calls the syscall. And so the idea is that if I call kernel 32 open process, I'll eventually call the nt open process syscall, which is what Dumpert, the Outflank team, figured out. But if I call the syscall, I don't call kernel 32 open process. And so what Outflank found when they made Dumpert is that there's a subset of, or there were at least, a subset of EDR vendors that were assuming that attack tools would only call these more superficial API functions. And so by calling the deep down syscall, they were able to evade detection. And so now we have a question in our mind, right? When we think about perception, so how do I perceive what's happening in my network environment, right? We think about the telemetry that's being generated by our EDR, for instance, right? And when we think about the telemetry that's being generated by our EDR, we think about it, or we think about it as if we're perceiving at the operational level. So I have a few different events that, and we'll talk about what they are and how we think about them. So a sysmon event ID 1, we think about that as a process creation event, which means that if a process is created, we expect that event to be generated, right? If Windows Security 4688, that's also a process creation event. If a process is created, we expect that event to be generated. Sysmon 10 is a process access event. If a handle to a process is opened, we expect that event to be generated, so on and so forth. 4697 in the Windows Security event is a service creation. MDE has device registry events. Those could be seen as registry key creation events. Now, here's the problem, right? We think about it operationally, but operations are abstract. They're not real things, right? They're just a figment of our imagination. It's a way for us to group like functions together, functions that are doing the same thing. Attackers don't act in operations. They act in functions. Out mini dump, in order to open a handle, right, to do process access, which is what sysmon event ID 10 is supposed to capture. In order to do that, out mini dump calls kernel 32 open process. Dumpert, on the other hand, calls syscall int open process. And so the key is that if there's a discrepancy between what we think should happen with our telemetry, if somebody opens a handle to a process, regardless of what function they use, the sysmon event ID 10 should be generated, and how it actually works, we have a problem. And that's exactly what Dumpert found and took advantage of. And because that happened, we should be skeptical of what our telemetry is telling us or purporting to be able to detect. So I'll pass it to Johnny to kind of talk about this next part about how do we actually do the testing to validate our assumptions that we are actually seeing operations.
Yeah, absolutely. Thanks, Jared. Yeah, I think, to touch on what Jared's talking about, there's a big piece that we have to understand when moving forward in like what we're trying to test and how we should go about testing. And there's two different things we're trying to test here. That is, one, what is my telemetry coverage? So what does my telemetry generate given a certain operation, right? Like evasion can happen at multiple levels of the scale. And the question is if it's bypassing the telemetry generation piece, I'm not going to be able to detect on it regardless. So detection cannot happen unless telemetry generation is possible. Hence why we've broken up these two testing capabilities and we're kind of approaching them a little differently. So from a telemetry coverage perspective, again, we want to do this from an operational perspective. I want to know, whenever we saw Jared's operational map there, we saw process enumerate, process access, and process read, right? Those are three different operations. And within those, there are various functional levels, various functional variations. And so I want to know if I perform process access, is telemetry being generated and at what level, right? And so how we can go about that is testing the different calls that are being performed. And like one thing that's really nice too, say that you have a kernel call that's available, right? And a syscall into the kernel call is there. And you suspect generation is being done at that level, you could just directly either make the kernel call or the syscall. And if telemetry is being generated, then you no longer have to test everything above that, right? Because everything's going to lead into that, and then your telemetry is going to be there. And for example, like process read has 8 functional variations, and we hear things like mini dump, write dump, for example, read process memory, etc. Well, those actually all end up leading into the same kernel call. So if we can then test those functional variations and we can get it from the lowest point and we can see telemetry being generated, then we can say, hey, I no longer have to test mini dump, write dump. I don't have to longer test the, I think it's kernel 32 read process memory, because I know that it's generating at this level. And then we can start to go into the piece of detection coverage, which is more procedural based. I want to know, given a specific technique, is my detection going to fire? And the reason why I want to look at this from a procedural standpoint and not an operational one is because there are various operations that can be mirrored in multiple different attacks. So like, for example, we're talking about cred dumping today, and dumping LSAS is our like core example. However, process access is very much used in process injection, for example. So if we were to do it from an operational standpoint, we wouldn't know exactly what we're testing in terms of detection, and we might have a whole bunch of different detections firing, and that's not necessarily what we want. We want a procedural based type of test, which is basically going to give me an insight into what procedural variations are possible, right? So like, if I were to call, let's see, like NT query system information for process enumeration, and then kernel 32 open process, and then I call mini dump, write dump, right? And that fires a detection, right? But then for some reason, if I did everything, but I changed and I called the syscall for the read process memory, and that doesn't fire a detection, I have a bigger issue there. And so although telemetry exists and we've determined telemetry exists, but my detection is no longer firing, there's an issue. And the nice thing too is if we can start to build out these procedural variations, one of the biggest things that I think we're asked at SpectreOps, a consultant company, is how do I determine my coverage percentage, right? Like a lot of people, I think, like blanket statements say, well, I have an 80 to 20 ratio in terms of detection gap coverage. And the problem is we don't know what 80% is until we know what 100% is. And so we have to dive into what those functional and procedural variations are. And once we understand that concept, we can build out what 100% is. And then we can answer the gap of, okay, this is what 80% coverage looks like. And then we can move forward that way. Next slide, please, Jared. Did you have anything you want to add there?
Nope.
Okay, cool. So when it comes to public testing solutions, it's quite nice because there are a couple of open source capabilities that are out there. Both of these tools that we're going to be talking about are both started by Red Canary and are very open source, and so you can go actually dive into the code themselves. And so the first one is going to be Atomic Red Team. This was started by Red Canary years ago, and it was meant to test security products and the detections and that they were firing. Right? It's explicitly, if you look at the README, it's explicitly meant to test detection coverage. Right? So we talk about different types of testing. We talk about what we're trying to test, and they've been very explicit and said, detection coverage, right? And so that's the problem they're trying to solve. And the not necessarily a problem, but an evolution as we've gone through this testing theory and going through and wanting to figure out what we want to test, we've identified that Atomic Red Team is more focused on tool versus operation, right? And so we'll talk about that here in a moment, but there is a newer solution out there that I think kind of solves that problem a little bit better, and that is atomic test harnesses. And this was started by Matt Graber at Red Canary, and this allows for very granular control over what am I trying to test. So am I trying to see if I'm going to get a detection fired for X technique, and then how am I going to do that? So it gives me granular control over the variational capabilities that might be there, right? So like if I'm talking about cred dumping, I could choose in the process read variation, I can choose the different APIs that I want to execute whenever trying to perform that operation. And this just allows me to be more granular and not only trying to test telemetry capability, but also moving forward into potential detection capability. Now, we're not going to be talking about the detection coverage and solution there yet, because just to be honest, we don't know if we've necessarily solved that problem quite yet, but we're going to be looking into the telemetry coverage piece here explicitly. And that's the reason why we're so focused on that, is we truly don't believe that you can answer the second question of detection gaps and coverage until we've answered the telemetry generation coverage question. Next slide, please, Jared. Cool. So whenever we talk about the operational differences of process access, we walk into, and Jared showed a similar view like this earlier, a similar image, and we see that there is one call stack flow starting at open process, and then that leads into an API set, an undocumented function, and then a native function inside of NTDLL to make the syscall. And then there's also another capability where you just make the native ZW version of the NT function, and then it makes a syscall directly. And this leads us into there's 6 variations from an operational standpoint and a functional standpoint of how we can perform a process access test. So this workshop is going to have a lab, and so I'll sit here, walk through the steps, and then I'm going to just like manually walk through it and give you all the capability and kind of show you how this is done. So what we're going to do here is we want to test telemetry generation. You should have access to the Sentinel provided by DEATHCon, and inside of that you'll have MDE and Sysmon. I'm not going to be showing you the Sentinel view because I don't necessarily have my box hooked up quite yet, but I do have Sysmon and MDE personally, so I'll be able to show you the exact same things you should see. Okay, and so what we're going to do is we're going to go and navigate to Jared's process access test harness, and we're going to download that script, and that's a PowerShell script. And so after we download that, we're going to open PowerShell as administrator, and then we're simply just going to run that operation with the variant of kernel 32 open process. And so there's 2 questions we really want to ask ourselves. That is, what telemetry are we seeing with Sysmon and MDE? And you could take this inside, let's say if you have your own lab with your own EDRs, what telemetry are we seeing generated? We also want to push you to go a step further and try the other variants to see if there's any discrepancies in the telemetry once you change variations. And then another bonus question is start to identify the telemetry generation differences in some sensors. Hint, hint, for example, Sysmon has the event ID 10 for process access. And that's going to log every process access event as long as your config file allows for that. So as long as the operation doesn't conflict with the config file and doesn't exclude it, it should log it. However, MDE's has a, and I'll show this, has a open process API call event. However, that's explicitly only for LSAS. So there's generation, telemetry generation differences there, because we might want to know this from an operational perspective of whenever we move from maybe looking at this from a cred dumping perspective to a process injection perspective, right? Like that's something we'd want to know. If you'd stop sharing, Jared, I'm going to share my screen real quick and kind of walk through that test harness.
What do you think about just talking about the next lab as well, and then doing them both?
Oh, doing both? Yeah, absolutely.
Yeah. Okay.
Yeah.
Just
Cool.
to save us from the transition.
Yeah.
Okay.
Cool. And so if we want to look at process read variation, we see that there's 8 different ones. And this was what I was getting at earlier, is if you call mini dump write dump, and that this is a very common API that gets called with various different tools, that actually ends up calling read process memory inside a kernel base, which is an undocumented function, which ends up calling the nt read virtual memory inside of ntdll, which makes that syscall and transitions to the kernel, etc. Now, if you call read process memory, that's going to do the exact same thing, which is quite interesting, right? So we see that we have, if you think about it, like we have a lot of tools using mini dump write dump, and then a lot of people mention read process memory. Like Mimikatz actually allows you to perform both of those functional variations to perform the same operation. Now, what's interesting is those both lead into the same function eventually. So whenever we're performing an operational test and I'm looking for telemetry, the question might be, where do I want to actually test my variation? Do I want to go and start from mini dump write dump? Or do I want to start from read process memory? Or do I want to go as low as possible and see if telemetry is going to be generated from that perspective? Because if it's generated, let's say if I call the syscall, for example, and telemetry is generated at that perspective, I can assume pretty safely that the logging for that function is going to be done in the kernel. Now, how you know that for sure is 2 different ways. You either write a driver and you test that theory, or you reverse whatever sensor you're looking at that you would suspect that generation to come from. But if we're talking about just performing like tool-based testing, or not tool-based testing, but operational-based testing, then that's how we can do that. And if we go to the next slide, we're actually going to do another lab that actually, we'll go here first. And so inside of the process read test harness, I went ahead and showed a screenshot with this, and instead of walking through the code, like I will for the other one, the process access. But we can see whenever we do the testing for process read inside of the lab, there are, I believe there's 7 or 8 different variations here. I want to say there's 7, but you have the capability to perform many different ones. Now, keep in mind, inside of this test harness, this isn't only process read. There is a variational difference in allowing you to do like process enumeration differently with create tool help 32, and there's also a duplicate handle capability for whenever you want to copy a handle. That's something different. So really focus on the mini dump write dump capabilities and the read process memory capabilities that are there. And this allows us and gives us intentional testing. That's the real big key when it comes to testing. I want to know what I am testing, how I am testing it, so that whenever the telemetry is generated, I can trust it, because I cannot trust my telemetry inside my detection if I don't know how it's generated. And the problem with that is I can then no longer trust the detections inside my organization. And so if I were to suspect or go to somebody and say, hey, I detect dumping LSAS, what does that really mean? And I could actually go into more granular explanation on what that means from my organizational perspective if I know how the telemetry is being generated. Cool. So with this lab, what we're going to do is similar to the process access one. We're going to go to the Red Canary Atomic Test Harness page, and we're going to download the dump LSAS test harness. Now, this is going to have a process access piece to it. It has to, in order to actually perform the read aspect. But just really try to focus on that process read operation. And we're going to do the same thing. We're going to open a PowerShell as administrator. We're going to run it, and then we're going to look at the telemetry generated inside of MDE, Sysmon, and maybe other sensors. Now, we don't have control over detections, but a bonus question might be like, given the variational possibilities, how many detections would you expect this script to alert on in terms of your detections? And then how many does it actually, and why, once you go through those variational differences? Okay. So thank you, Jared.
One thing while Johnny's kind of getting the demo fired up, he touched on this, but So we want to know, the question that we're asking right now is, when my event, my telemetry, my sensor, my EDR tells me that it detects process access or that it generates events for process reads, should I assume that they're telling that they have full coverage, right? They may not even know that they don't have full coverage. And so when you make an assumption, you get hit with something like dumpert, and turns out that your assumption was wrong. Now you're in trouble, right? And so there's two ways to solve this. One is to either reverse engineer the binaries to figure out where the telemetry generation is actually occurring, and usually that's pretty hard. Or to use a dynamic approach like these test harnesses. So the test harnesses are basically, the idea is let's run through all the different variations, and then we could evaluate whether or not telemetry was generated for each variation that we presented. And if it is, then we can have fairly good confidence that our telemetry is telling us what we think it's telling us. Go ahead.
Absolutely. And keep in mind, there is a limitation to these tests, and that's because it is written in PowerShell, so it's leveraging pinvoke. And if you're not familiar with pinvoke, it is a way to expose the capability to call different APIs, like Win32 APIs, and some of those undocumented ones through .NET. But one of the issues that we've found, and we haven't found a great way to solve this yet because it's quite ugly in a programmatical sense, is calling the syscall within these task harnesses. So we're not doing those, so keep in mind, but we are calling the ntdll function, which ends up calling the syscall eventually, which transitions to kernel. So there is that piece, so keep that in mind. But ideally, you would make the syscalls as well to appropriately test these. So going back to the process access, right? So this is how you would run this. And let me go ahead and get Event Viewer started, because this is, if you ever deal with Event Viewer, it's a phenomenal way to look at logs, but it takes a minute to load up logs. So let's get that puppy warming up. Okay, cool, because I'm going to need that in a second. So what I'm going to do is I want to import process access. This is the first lab that we have for you. And inside of this, I'm then going to call, oh, wrong one, sorry. I'm then going to call invoke process access and then specify the variant kernel32 open process. Now, if you remember, this is the very first function within that function call stack that Jared was talking about. So there's other options, for example, right? Like if I wanted to call the ntdll version, I could do that. But for this lab, let's go ahead and just do the kernel32 just for the purpose's sake. And what's going to happen is that is going to reach out. This should be the LSAS process, if I'm not mistaken. Perfect, yes. So by default, this will be the LSAS process. Now, if we go inside of the event viewer, I suspect to see an appropriate event, sysmon, operation. What was my process ID? That was 3324. If I go ahead and filter here. Here we go. So again, I would, let's see, source image, this is incorrect. Let me go for the LSAS, looking for LSAS here. Alrighty, come on. Okay, let me just clear the log and do it again. For some reason, that's being a little difficult. Great, here we go. First event here. So if you can't see this, I'm sorry, I don't know how to zoom in on the event viewer, but here we go. So I have an event for PowerShell accessing LSAS with these access rights, which is 1410. And I could change that within the variation as well, I believe. Access right. So I could do something different. I could do query limited information, and I would suspect to see that as well when looking for those events. Well, that's going to be a little difficult to find here, probably. Almost there, probably. Let's see. Here we go. And so this is what we see. We see a different axis, right? Because I changed that. But the good news about this is that I can going through these variational differences from a functional standpoint and an operational standpoint, I can start to see the differences that, hey, Sysmon's going to log any granted access to any process, assuming that my config file is not standing in the way, and I can get this type of activity. Now, what's interesting is if we do this from a process read perspective, there is no process read based event within Sysmon, right? So this might be where we want to pivot into MDE. So let's go ahead and look at this. Now, I did this earlier, I'll show you what this looks like. It just takes a while for MDE. If you ever dealt with MDE, it takes a hot minute for that data to get ingested. But this is what that would look like if you were to run this test. You would see that the test ran appropriately, and I did theoretically dump LSAS by and read its memory by leveraging NT read virtual memory. Now, if I show you what that looks like inside of MDE, give me one moment, please.
One thing to mention too, while he's pulling that up, I recommend like going through the different variants and evaluating. So Johnny's only just because of time for the presentation, he only showed one variation. But generally speaking, as you're playing with this, go through each variation, and you could use those function call graphs in the slides. Those should be shared with you to kind of see. Okay, which one should I run first? Maybe run the most superficial one first, and then kind of work your way down the call stack and say, okay, kernel 32 open process, that works. API set open process works. Kernel base open process, that works, and kind of work your way down. So kind of work through all of them. You should be able to type in -variant and then push tab, and it will tab complete for you. So you could just kind of iterate through them. Go ahead.
Absolutely. Yeah, thank you, Jared. So with that, so I did do this previously just so I could get MDE again. There is a really cool event within device events, an action type called read process memory API call. What was interesting was earlier I was testing MDE and like running through all the different variants, and I did call the NTDLO one, and I did get an event here. And this is the event that we can see within it. Now, the metadata is maybe not the best, but what I do see within here is that I did have a PowerShell process that did read LSAS's did read the LSAS memory, and so that's good to know. Now I know that whenever I'm starting to create my detection rules, that generation of that operation is going to be exposed through that operation is going to be exposed through MDE in some type of event, and that's really cool to see. Another one I wanted to showcase was the open process API call. This is what I was talking about earlier. Was I was doing some testing, and I went ahead and went and pulled or accessed another process that wasn't LSAS. However, all that I'm getting are LSAS events. So that's good to know whenever I'm going through my detection process, and I think, hey, Sysmon's going to expose to me every process access operation as long as my config file doesn't get in the way. But it looks like the open process API call is only going to expose to me the LSAS or any process accessing LSAS. So when dealing with Sentinel, I really urge you to try to maybe run these and then check to see the coverage. And what's cool is go ahead and check the coverage that is exposed in terms of what the Sysmon config through DEATHCon is exposing, and see if there's any data that's being suppressed through the config file as well. And that's good for us to know. And then you can play with what telemetry is exposed and then move on to that detection aspect. So again, we were talking about moving back into Atomic Red Team. One thing that we found when diving through this was, again, the reason why we want to touch on Atomic Red Team is it's a phenomenal tool. It's exposed to us publicly, but maybe testing and how testing should be done has evolved over time, and that's okay. I don't think we would be at where we're at today if Atomic Red Team didn't exist previously. Like, that's a really cool thing about our industry, is we don't get to where we're at today unless someone did something prior, and now we can then evolve. And what's interesting is if you look at the credential dumping atomic tests, there are 12 tests, and we can see the different names of the tests. We can see proc dump in here, but what's interesting is we start to see some similarities. Like, we see proc dump in here more than once. We might see mimikatz in here more than once. So the question is, what is changing from a variation perspective? Is it a functional variation? Is it really just a tool-based variation? What is changing here? And then I can then figure out how to apply that testing appropriately. Next slide, please, Jared. So testing the differences between atomic red team and then the atomic test harnesses. So there are 12 total tool variations, meaning that they say there's 12 different tests inside of there, and there should be 12 different base tests. But what we found was I think there's actually like 10 different tools actually being used, and so that means there's repetitive tools within the different tests, and there's only 2 of 8 process read functional variations, and those are going to be the DBG help mini dump write dump and then the kernel 32, so the highest level of read process memory. Now, what's interesting is 10 tools that are being used within the tests are all using mini dump write dump. So when I'm thinking from an operational testing perspective, I'm not getting much of a difference or much of a test difference in terms of what is my telemetry generating, or can I really test my telemetry? Because I'm really just getting the highest level of both those API calls, not the lowest level one. So theoretically, let's say we had a defensive project that was hooking onto both those APIs, I would see the telemetry, I would feel good. But then if we use something like a lower level call, like a syscall, and that didn't generate telemetry and I didn't know about it, then I couldn't necessarily trust my detection moving forward, right? And so then we have 4 functional variations. I went through and kind of through the code and figured out what the differences between all the different tests were, and there's only 4 functional variations. And so what's interesting is we see 6 of them, however, are leveraging the NTDLL, NT query system information, kernel 32, open process, and the DBG help mini dump write dump. And again, this is interesting because if we're talking about functional variations and procedural variations, this doesn't give me a great idea of where I'm at, not only from a telemetry perspective, but from a detection perspective as well, right? It limits what I think I have versus maybe what the reality is what I have. And what's interesting is I understand why the tool variations are exposed and are being tested upon, because it could be a good thought that if we just take a whole bunch of different tools that we've seen in the wild, expose them and test based off those, then and my detections cover all those, and I should be okay. The problem is if we haven't gone through those functional variations, then we're limited to what has been exposed to me publicly, right? Or the operation or the tools that are exposed to me either natively on Windows or publicly in general. I don't have the granular control to go deeper, in which terms I would then have to go create my own tool and then test that theory if one didn't exist.
Just to add to that, so there's potentially a number, and we'll get into this. We'll get into exactly how many functional variations there are for credential dumping, or at least this operational sequence, right? So the operational sequence is process enumerate, process access, process read. How many functional variations are there? We could actually answer that question. In this case, we see 4, right? And there's this fallacy that I think that a lot of us fall victim to where we think that more tests means better coverage, right? But when we start to actually peel back the superficial layer, the veneer of the tool, right? Remember the tool, the changes between tools like out mini dump and sharp dump, those are minimal, the differences between them, because they call the same functions. And so the idea is that, yeah, is it valuable for us to compare, like to run out mini dump and sharp dump even though they're functional synonyms? Yes. The reason why it's valuable is that helps us eliminate the possibility that we're doing a tool-based detection. That, for instance, our detection is built targeting out mini dump so much that if any change happens, we're going to miss it. But after you do 2 functional synonyms, you start to lose value in each subsequent functional synonym. So like when we see, for instance, 6 variations of this second functional variation, 6 tools that implement the same functional variation, we realize that number 3, 4, 5, and 6, we actually are getting very limited value because they're too redundant, right? And so the idea is that, yeah, maybe you could only run 12 tests. Like, I don't know if 12 is a good number or too many or too little, but ideally we want to get the most bang for our buck, right? And as we're running the same functional variation over and over, we actually aren't getting the bang for our buck, right? And so the idea would be we want to maximize the coverage of functional variations. And that's where we go to that representative sample set that I talked about. It's like we want to make sure that we're representing as much variation as possible. And you don't get that just from looking and seeing that the tools are different, because tools could be different literally, but they could be functionally equivalent. And so I would rather, for instance, be doing operational synonyms than just a bunch of functional synonyms, for instance. Go ahead, Johnny.
Yeah, thank you, Jared. And then we move into the atomic test harness piece, which we're looking at the operation and process read, and we actually get 6 out of 8 different functional variations. And the reason why we don't have 8 out of 8 there is simply because it doesn't support syscalls right now, and it doesn't allow us to call the direct kernel either. So there is a limitation there. However, I would rather have 6 out of 8 than potentially 2 out of 8, right? And so that is a better sample set of testing that I can apply and then confirm that my telemetry is being generated. Now, again, we'll talk about this in a couple slides, but, like theoretically, you could have, we've seen some operations have like tremendous amount of functions that could be used in order to get, like, process enumerates one of them. It is you could have many functions that could do that. However, it does lead into, I think, 2 or 3, correct me if I'm wrong, Jared, 2 or 3 underlying functions that get transitioned. Now, what's interesting, I really want to drive this point home, is we don't necessarily have to do all the call stacks starting from start to bottom. What we want to do is bottom to top. And so we want to test the lowest level of the operation, because if we get telemetry generated for that, then I can assume, or I know that everything above that, since it leads into that call, I'm going to get telemetry. And so that's really a key piece there, instead of having a hit or miss. Like, oh yeah, like it's interesting because I've had many people send me different LSAS dumping tools, and I've looked through them and I'm like, oh, this is functionally the same as other ones. Like, this isn't a new, even though it's a new tool, it's not a new way to dump LSAS, right? And so what I'm interested in is finding the operational functional differences, and that way, like the new really cool one that just came out that we didn't account for because we didn't have time to necessarily do the research on it yet, is it was done at DEATHCon. It was called, I think it was LSAS stinkering or something like that. Really cool way of using APC calls in order to dump LSAS, which is really cool. And that would be another operational variant, right? And so we'd want to apply and look into that, because once we start to, it's an easier pill to swallow, an easier problem to solve if I were to look at the operational functional differences between all these tools, which we've identified. Let's say, like with atomic test harnesses, like 12 tests, there's only 4 functional variations, and there's only 2 out of 8 process read functional variations, right? What I'm curious about whenever something else comes out is there a operational functional difference there? If not, and I know telemetry is generated, and I know we've stepped further into the detection route, which we're not necessarily answering today, that I have a detection firing for that, ideally, then I should be in the clear. Like, I would no longer have to perform all this various testing. I feel comfortable with that generation of the telemetry, and that's the key. We can't trust the detection if we can't trust the telemetry. And so we need to know what we're testing. We need to understand how we're performing the testing. And then whenever we move forward, we are more confident in the telemetry being generated. And then if things aren't being generated, we could go to our vendors and say, hey, why am I not seeing these events? Is there a suppression happening behind the scenes that I am not aware of, etc.? Next slide, Jared.
Yeah, so one of the things that we talked about is, hey, we have 4 functional variations, but we don't know, is it, like, we knew that there's, okay, so it's worth noting when I'm kind of using functional variations to mean 2 different things. So within process read, right, the process read operation, there's 8 different functions that will allow you to achieve the process read operation or implement the process read operation. In this case, we see that Atomic Red team demonstrates 2 of the 8 process read functional variations. But then there's also, maybe they should be called operational variations. I think Johnny had that and I changed it, so that's on me. But which is the combination of functions that allow you to achieve a technique, right? And so in this case, like for instance, we see kernel 32 create tool help snapshot, which is different than, for instance, this one, which calls ntdll, nt query system information. But you can, you can change any of the functions and like within any of the three operations to get a different variation, right? And so we could actually start to calculate how many possible variations there are, right? So if we've looked through, for instance, we made those function call graphs, which was, we saw that there was like, kernel 32 open process calls the API set open process, which calls kernel base open process. Each of those is a variation. And so what we could do is we could say, okay, well, we know from an operational perspective that the attacker has to enumerate processes to get the process identifier. They have to open a read handle to LSAS, and then they actually have to read from LSAS. But we also have evaluated or enumerated at least a large subset of the possible functions that will allow you to achieve each of those. And so what we found is that process enumerate has at least 21 that we know about, 21 functional options. Process access has 7 functional options that we know about. And process read has 8 functional options that we know about. And so we can use simple math. What you do is you say you multiply the possibilities of each but times each other, right? So there's 21 process enumerate options, there's 7 process access options, and 8 process read options. And if you multiply 21 times 7 times 8, you get 1,176 possible variations of functions that you can combine together to achieve this outcome. But if we look at what Atomic Red Team is giving us, we have 4 out of 1,176. That's not an indictment on Atomic Red Team. Atomic Red Team's a great project that put us in the right spot. But now we're coming up with maybe a more sophisticated way of representing the variance, and that allows us to inform projects like Atomic Red Team to take a different approach. Maybe it's not so much about, hey, these tools are different, but it's a matter of how the tools are different, because certain tools are more different in a way that makes them more valuable. And then we could use things like atomic test harnesses to simulate versions or variations that maybe aren't represented in a known attack tool. So like we have Mimikatz, and that is what it is, but maybe there's a possibility that some future variation is going to arise, like Dumpert, right? That we don't know about, but we can predict it because we've enumerated and built out these function call graphs. Okay, so you wanted to add something?
Yeah. One thing I wanted to add onto this as well is when we talk about operational testing, it seems like a big pill to swallow as well to say, oh man, I got 21 process enumeration, 7 process access, etc. But the one thing I want to note, when you do testing telemetry wise, like you don't have to do that every time you encounter a new technique, right? You're like optimizing your time, because really what's cool is someone on Twitter, I believe maybe it was Roberto Rodriguez, correct me if I'm wrong, Jared, made a mapping of all the different modules within Mimikatz that leverage process access. And so if you go,
Demetrius is his name, but I don't know what his last name is, but
okay.
Yeah.
The point is, what you find is the same operation is leveraged in a lot of different procedures or sequence of operations, which Jared will get into. And what that allows me to know is, okay, cool. It doesn't matter if it's used for dumping LSAS or process injection. I can get process access telemetry, whether that's through Sysmon, whether that's through MDE, etc. And then where I know my telemetry stance is at, I can then move forward into the other questions like procedures and detection.
And the cool thing is that there's actually a finite number of operations, like a relatively small number of operations. The thing that makes a technique unique is how those operations are sequenced, right? This is actually similar to DNA, right? So how proteins are sequenced matters, not just what proteins are there. It's like the order in which they're sequenced. And so like process access, like Johnny said, it's it's LSAS dumping, it's process injection, it's access token manipulation. It's going to be used all over the place, right? And so what we can do is we can start to, like, once we figured out that like Sysmon Event ID 10 is what we're relying on, and we know that that's going to fire no matter what function is chosen, we never have to worry about that again. We just have to do it once. And now we can apply that to numerous numerous detections. But, okay, so we're at the point to where we've enumerated or identified that there's 1,176 different possibilities, and we're currently only detecting testing 4 of them with atomic red team tests. Now, I don't think that you need to be testing all of them in order to get a good idea of how well you're detecting things, because some functional variations are more different than others, right? So the Dumpert variation is more different from out mini dump than potentially some other one that's just slightly changed, right? There's some ways to measure that. We don't have time to get into it, but maybe in a future blog post or talk, we could talk about how to measure the difference between functional variations. Okay, so atomic red team's not the only one. We wanted to make sure that it doesn't appear that we're picking on atomic red team, and we're looking at a second example of this. Both of these are great, right? Like AV Comparatives is this organization that basically runs through and looks at different antivirus products, and in this case, Microsoft's EDR, so Defender for Endpoint, to evaluate how well they provide coverage. So in this case, it's visibility, detection, and prevention of different things, right? In this case, they were looking at credential dumping. And what we see, like I actually think AV Comparatives had a really good write-up. You can see there's a PDF for the report at the bottom. They had a really good write-up. They had a good methodology. But one of the places that they had they ran into a fallacy, in my opinion, is the same place with Atomic Red Team. And this is the same place that I think the entire industry has a problem, which is why we're talking about this, to where they assumed that because they had 15 tests, they were presenting enough variation to have a representative sample. But one of the difficulties with this analysis is we don't necessarily get enough information or direct links to the code that they use to implement this. So we don't know exactly what all of these correspond with. Like, for instance, what is dump LSAS? I don't know. But we do have enough information that we can do some kind of superficial analysis. So, for instance, we see test 1 is Mimikatz via process herpaderping. They have test 8 is PowerShell Mimikatz. Test 9 is invoke Mimikatz. Test 14 is invoke Mimikatz via PowerShell Empire. So, we know enough about how those work to be able to say that those are all functionally equivalent. So we know that there is also some redundancy being run into in this case, right? So, basically the idea is that this is not unique to Red Canary or the Atomic Red Team project. It's a problem the entire industry is running into, and we currently don't have we haven't traditionally had a way to be able to evaluate similarity, right? And so we've been relying on quantity as opposed to quantity and quality, right? Or the difference of things. And because some tests are going to be more different than others, which provides you better coverage or better approximation of what the problem actually is. Okay, so thus far we've only talked about what I call the primary or orthodox procedure of memory dumping, LSAS memory dumping, which is process enumerate. We need to get the process identifier or the PID for LSAS. Process access, we need to open a read handle to LSAS, and process read. But through our analysis, we've actually identified 4, and then Johnny talked about LSAS stinkering, which we think is a 5th. We haven't done the analysis to validate that, but we read enough about it that we think it's a 5th variation. But at the operational level, or what we call the procedural level. So I think of, each individual circle here is an operation. It's a thing that's being done, but when they're combined, to achieve some technique, that sequence of operations becomes a procedure, right? And that's my way of viewing procedures or defining procedures. I have a blog post about that that's linked at the bottom of the slide. But what we found is that there's actually 4 different procedures that are implemented. So, for instance, the famous one is James Forshaw created a bypass evasion to where what he does is he enumerates LSAS, then he opens a process duplicate handle instead of a process read handle. And so there's a lot of people, for a bunch of different reasons, that are expecting a process read handle to LSAS to be generated. And so he's like, well, can I avoid doing that? And so what he does is he creates a handle, but it only has the process duplicate handle right. And then what he does is he found that there's a flaw or maybe an intended use case to where you can convert a handle with only the duplicate handle access right into an all access handle by calling basically int duplicate object. And so that's what he does here, and then he reads from that duplicated handle. There's another one that was, I think, created by Bill Dimmercappy, who basically opens a handle, then he opens a process create handle to LSASS, then he creates what he calls a forked process, and then he reads from the forked process. And so that just creates enough difference to throw off a lot of detections. So anyway, so what we're able to do is we're able to apply this same math, right? Which the orthodox kind of procedure has 1,176 different variations. But if we were to apply that same math to all of these different procedures, we would find that there's 39,333 functional variations, of which we're only representing 4, right? And so that we're starting to get an idea that maybe that's not enough to satisfy our question of how do we know that we've detected this? So I've been thinking about this categorization problem. Like, right, we have multiple layers of abstraction, and the big question is what level of abstraction is correct, right? So at the literal level, right, so literally different tools, there's an infinite, or, you know, at least something that's approaching infinite or something that's unknowable. There's an infinite number of variations. So there's an infinite number of tools that can be created that would allow you to implement LSASS credential dumping, right? But we've grouped all of those tools into one sub-technique called LSASS memory dumping, right, within MITRE attack. But like the literals, you know, literal is so much that we can't actually do anything with it. So I have this, I'm kind of going out of order, but I have this here. It's like if we test one tool out of infinity, then we basically tested the equivalent of 0% coverage. If we test 100 tools out of an infinite number of possibilities, we're still at 0% coverage. If we've tested 1 million out of infinity, infinity is so large that 1 million is approximately 0. And so if we have to treat it as if there's an infinite number of variations, we make no progress, right? We can never solve the problem. However, we all know, based on the idea that things like atomic red team exists, and we, you know, it's popular, right? So we all know that treating all of these different tools as if they're just one thing, that's too abstract. So we've reduced the number of possibilities into too small of a number, right? So if we can't just take one tool off the shelf, test it, and be like, yep, we're good, we cover that. We all reject that kind of logically, right? And so there's this scientist from UC Berkeley, Eleanor Rush, who in a paper that she wrote in 1976 on categorization theory, she says that one purpose of categorization is to reduce the infinite differences among stimuli. In this case, the stimuli are the tool instances that we can use to dump credentials. Reduce the infinite differences among stimuli to behaviorally and cognitively usable proportions. We can't comprehend an infinite number. And so what we have to do is we have to use abstraction to allow us to group things that are similar in ways that we can reduce infinity to the finite. And so what they say is categorization allows us to ignore insignificant differences, right? We could remove all the insignificant differences and say those don't matter. And so although those differences make these things literally different, they don't matter for what we're trying to achieve. And so we can ignore them, and we can reduce infinity into 39,333 different differences or different variations. Or we could reduce 39,333 variations into 4 variations at the procedural level. The question is, what level of analysis is appropriate for detection? Okay? What we're proposing with this talk and with the atomic test harness approach is that if we can validate that our telemetry will produce events regardless of what function is being used. So for process read, there's 8 different functions that we've mapped out. So there could be more, but we at least know of 8 different functions, right? If we can identify that our event that we rely on for process read, for knowing that a process read took place, will be generated no matter which of those 8 functions are called, we could then ignore those differences, right? And so this is why we think the atomic test harness approach is the first step towards being able to actually comprehend our detection, right? So if we could ignore the differences between the function that's being used to achieve process read, or the function that's being used to achieve process access, or the function that's being used to achieve process enumeration, then we could reduce 39,333 different variations to 4. And 4 is a number that we could start to wrap our heads around, right? And then what we do is we take those 4 variations and we make sure that they're represented by our atomic tests. And then we can have a pretty good understanding of how well our detections are actually performing against the possible variations or against the representative sample set of variations. And that's the approach that we're trying to get towards with leveraging categorization, leveraging abstraction to be able to take the infinite and reduce it down to 4 variations in this case. Maybe I've looked at, token theft, and there's 29 procedures for token theft. And so, yeah, that's more, but 29 is still manageable. It's not 40,000. It's not infinite, right? And we can start to get an idea for what's going on. So I don't know, Johnny, that's what I have. I don't know if you have anything you wanted to conclude.
Well, one thing I wanted to say too is back to my original point. Like, we look at the functional level for wanting to test telemetry, 39,000. That seems like a lot, but we don't. Again, and I'm really trying to drive some. We don't have to go top down. We don't have to go from the highest level API down. Ideally, we go down up. And so in this instance of dumping LSAS, we're dealing with those different operational sequence or the sequence of operations. But I want to test at each one of those operations where is telemetry being generated. And if I can get each one at a kernel or syscall level, all of those other higher level API functions are going to funnel into that. Yep. And then I can go ahead and identify, okay, this is where my telemetry is being generated. I don't have to go test the other potential 20s of functions that are above that, right? I can go ahead and just say, hey, this is where it's at. But it's good to know. The reason why it's nice to go from down up too is if you go to the kernel and you're like, or you make a syscall and it's not being generated, you're like, I wonder why, right? And then you go up a level and then it's not there, and then you go up another level and it's there. API hooking maybe is being done, or there's another type of telemetry generation mechanism being done, but we need to know where our gap of telemetry is. And so if we know it's possible for someone to call something lower, then we need to identify that and maybe either talk to our partner in terms of whatever we're using for telemetry, and get them to maybe like expand upon that or switch where we're getting our telemetry from.
You could think of the function call graph as being like a tree, right? So you have the syscall is the trunk. The trunk is the interface between above ground to underground, right? And so the trunk is the syscall. That's the thing that everything funnels through the trunk, right? And then you have major branches, which are the native API calls. You have minor branches, which are maybe the undocumented API calls, and you have the leaves. And the leaves are the current, like the Win32 API calls. Those are what Microsoft expects you to interact with, but you're not limited to interacting with those. Yep. And the idea is that if you could validate that logging, I guess pun intended, is occurring at the trunk, you could assume that if somebody enters at the leaf, it's going to work its way all the way to the trunk, right? But if you only validate that logging occurs at the leaf, you can't assume that it's occurring at the trunk. So
yep.
That's kind of maybe a mental model for you to take away from this. But anyway, this has been our talk, mapping. What do we call it? Mapping detection coverage, maybe.
Yep, something like that.
Something like that. We kind of made up the name right before we started presenting, so I've now forgotten what it's called. But anyway, this is our presentation. The general idea here is that we can use abstraction to reduce the infinite into the finite. And if we can identify what level of abstraction we can, but like the idea is that some level of abstraction, differences at lower levels cease to matter for the purpose at hand, for the thing that we're trying to achieve, which is detection. And what we're proposing is this idea that by using things like the atomic test harness to validate event coverage, telemetry coverage, we can begin to eliminate not only the literal level of analysis, which is infinite number of possibilities, but also the functional level of analysis, which has 40,000 variations in this case. And we can focus at the procedural level of analysis, which only has 4 different variations. And that's extremely advantageous to us. And then we can implement that in our kind of breach attack simulation testing suites, right? So whether that's Atomic Red, whether that's something homegrown, or whether that's a commercial tool that you're using, that's an approach that we can start to take. So thank you, everybody, for your time. Again, Jared Atkinson and Jonathan Johnson from SpecterOps. Appreciate it. Looking forward to any questions, any further carrying on of conversation around this topic. Happy to engage. So thank you, everyone.
Absolutely. And if you have any feedback whatsoever, please let us know. Like, this is something we love to build upon too. So feel free to start conversations with us about this topic, because we like it quite a bit. It's been a focal point for our research for a little bit. So thank you guys so much.
Cheers.